Hello and welcome. Today I want to speak to you about some basics of hydrogen 1, H1 NMR spectroscopy, specifically with reference to the kinds of questions that students would have to solve on IB chemistry standard level exams. So here we see an image of an NMR spectrum machine, which it's quite a complicated device. As the name suggests, nuclear magnetic resonance. So there's the need for a magnetic field that is going to influence the nucleus. The nucleus of what? Because it's H1 NMR, it's going to be the nucleus of a hydrogen atom that is being influenced by a magnetic field. Now, students of IB chemistry do not have to explain the workings of the NMR spectrometer. What you do have to do is to understand the language that's associated with the interpretation of the NMR spectrum and how to interpret the NMR spectrum. So a good starting point to get an idea of what's meant by de-shielding and shielding and upfield and downfield is to look at the standard molecule tetramethylsilane, TMS as it's called. And while the structure and the uses of TMS are not required for SL, it's required for HL, it's a useful starting point because here you will see in TMS, which is made up of silicon in the middle and 4 CH3 groups, it's a very good way for us to show 12 hydrogen atoms that are in a chemically identical environment, meaning to say the nucleus of each of those 12 hydrogens associated here, 4 multiplied by 3, 12, all of those hydrogen nuclei will be influenced by the magnetic field in the identical manner. So they will give one uniform signal, and that is what would give us the starting point or the calibration point for NMR spectroscopy. A huge peak from those 12 hydrogens at chemical shift value equal to 0. That chemical shift value, you don't really need to know what chemical shift means or what unit it is. You see it's usually written in parts per million. But now let's get to an understanding of what you, the student, would have to do in the examination. And here we have now 2-methylbutane, as you can see, bute because 1, 2, 3, 4 in a straight line, and a methyl group there on carbon atom number 2. What is its NMR spectrum going to look like? And while TMS has one signal for its 12 hydrogens, 2-methylbutane is going to have 4 different signals because there are going to be different extents of shielding and de-shielding happening in the molecule because each of these hydrogens here are in slightly different chemical environments. Let's break that down for you. You see, the hydrogens associated with this carbon A and this carbon, which we'll also call A, are in a chemically identical position. Each one is attached to a carbon, which is in turn attached to a hydrogen, which is then attached to another hydrogen, which is in turn attached to a CH3, which is then attached to C2H5, all of this. And the same description applies to this one. This is attached to a carbon, attached to a CH3, attached to a hydrogen here with the carbon, and then a C2H5. So you have one chemical environment with 6 hydrogens in environment A. That's equal to 6. Then you have 3 other environments. It might be useful for you to think about where those environments are right now. Another environment is this hydrogen right here. Let's call this hydrogen B. Because it's in a special environment, there's nothing else there in this structure that's attached to a carbon and then in turn having that attached to this, and this. Chemically unique position for that hydrogen. Then these 2 here, C, they are in a chemically unique position. And of course, D. So it's really all about where the hydrogen is in the molecule. And to contrast this A, B, C, D that we have here, these four environments, let's just go back for a bit and look at TMS. TMS has a 12 hydrogen signal at chemical shift value equal to 0, and that's taken advantage of in setting a 0 point or standard on the NMR machine. For HL students, if you're an HL student watching this, TMS also has other properties. It's highly volatile, so it gets out of the machine very easily. It's not very reactive, and of course it gives this nice, big, distinct signal. But getting back now to 2-methylbutane, we will see that one hydrogen environment has a signal of 6, another one B, a signal of 1, another one C, corresponding to 2, and finally D, corresponding to 3. So what we will get for the low resolution, and HL students have to do high resolution, but SL students, you only need to study this at the level of low resolution. So the low resolution NMR of 2-methylbutane will have 4 distinct peaks somewhere along here to the left of the TMS signal, and those peaks will be in the ratio of 6:1:2:3. Where exactly they will be, which ones will be more downfield or upfield, or more de-shielded or more shielded, is difficult to say, because 2-methylbutane is full of methyl groups. So you would not be expected to talk too much about shielding and de-shielding in a molecule like 2-methylbutane, but you might be expected to talk about it in a molecule like ethanol. Now, if you've been following the explanation so far, you should realize immediately that ethanol is made up of 3 distinct chemical environments. Here you have hydrogen in this chemical environment, and it's all about hydrogens, by the way, because it's the H1 NMR spectrum. So we're just looking at hydrogens. These 3 are in environment A. You have 3 hydrogens. Then you have environment B. So these are here A. Then you have environment B with 2 hydrogens. And very significantly here, with this hydrogen over here, you have that in one hydrogen in that chemical environment C. Now, because oxygen is a very electronegative element, the electrons in this covalent bond are held much closer to oxygen than it is to hydrogen. What that does is it de-shields, it exposes hydrogen's nucleus to the magnetic field. And this hydrogen here, this one, C, would give a signal in the NMR machine that is very much downfield because of that de-shielding. So it will be somewhere on the downfield side. The data booklet will give you an idea as to exactly where that would be, but it's going to be somewhere downfield. Then hydrogens in environment B are also going to be a little bit more downfield than the ones in environment A, because environment B is closer towards that OH group there, and that too is going to have some effect of de-shielding, pulling electrons this way. And signal B would be a little bit less downfield than signal C, and finally signal A will be the closest then to TMS. And that is how you interpret the low resolution NMR spectrum of ethanol and 2-methylbutane.